I'd like to introduce our panel. We have Jeff Sheehy from NASA headquarters. He's in the Space Technology Mission Directorate. He's a senior technical officer. We have Mark Adler from JPL. He's the project manager for the low-density supersonic decelerator. Jason Crusan is the director of the Advanced Exploration Systems Division at NASA headquarters. And Nantel Suzuki is the program executive for Lunar Lander Technology in the Advanced Exploration Systems Division. So we'll start with Jeff talking about a lot of the technologies that our Space Technology Mission Directorate is developing to enable human exploration and supporting our missions to near-Earth asteroids and eventually sending humans to Mars. So, Jeff.
Oh, well, thank you very much, Chris. I'm glad to have the opportunity to be here and give you a little bit of an overview of what we're doing in Space Technology Mission Directorate. We were formed as a mission directorate about a year and a half ago, maybe not even quite that long ago. So we were a program within the Office of the Chief Technologist before that. We've been funded for maybe 2.5 years, getting on toward 3. And so a lot of the projects that we started initially, including some activities that had been initiated under other auspices within the agency and that were collected into the new dedicated space technology activity, are bearing fruit. And so I have the happy job today to be able to show off a few of the projects that are delivering test results. So we're creating new technologies, we're producing new data and new information, creating new knowledge, and we'll see some of that come to fruition over the next several months, and some of those results are already in, so that's great. So what I aim to do today is give you just a little overview of who Space Technology is and sort of our program structure and the main areas of emphasis, hit some quick highlights of different projects we're working, supporting Mars exploration, supporting SLS and Orion, and supporting planetary exploration, and then show you a little bit more detail on some of the test results that are in, and then I'll yield the big triumphant show of results to Mark Adler, who has been leading a project under our mission directorate that just had an overwhelmingly successful test flight. So space technology is organized into 9 different programs. I've listed them here and given headings to them in terms of transformative and cross-cutting technology breakthroughs, pioneering concepts, and creating markets and growing the innovation economy. So over here on the right-hand side, or left-hand side, close to me, you have technology demonstration missions. This is our centerpiece, large demonstration program. So taking technologies that they're at 5 or 6 on the technology readiness scale that NASA uses, advancing them to a point, typically in a system-level implementation, where they're ready for infusion into some mission, some actual NASA mission or some other government agency or industry use. And so the idea there is to kind of cross that valley of death between development, you've done what you can do in the lab, and demonstrating frequently in space flight that this system will really work and somebody can pick it up and use it in their mission. So we've done that sort of demonstration. Projects in that technology area included deep space atomic clock, laser communication relay, that's optical communication from Earth orbit to the ground and between orbiting assets. There's a solar sail demonstration, the low-density supersonic decelerator that Mark leads, and several other activities of that nature. There's a green propellant demonstration. I'll show you a little bit of a hint of results from that one as well. The small spacecraft technology program looks at what can we do with small spacecraft. Several people that I've met here have come in from the small spacecraft conference that was going on earlier this week in Utah. And the small spacecraft community and the small spacecraft implementation activities are just growing and growing by leaps and bounds over the last few years. People are recognizing that as sensor technology develops and propulsion technology for small spacecraft matures, and we can do more and more with those assets that have very low launch costs. We can replace them when they age out rather cheaply. And we can use gangs of them to do jobs that may have taken one monolithic spacecraft previously. So we have several activities in there. We have 4 launches coming up over the next 18 or so months of different technology demonstration: communication, navigation, proximity ops, propulsion, all the different technologies that you need to make heavy use of small spacecraft for actual mission implementations. Our game-changing development program is a large activity that takes things from concept and through that initial laboratory implementation, small-scale implementation, to determine whether the concept really is valid. And so that's the technology readiness level from 4 to 6, kind of the mid-technology readiness level. I like to think of things as development and demonstration, but preceded by discovery. So this middle column here is really more of a discovery effort. So going from discovery to development to demonstration, we have the NASA Innovative Advanced Concepts program. That's really concept studies for typically some rather far out sorts of things that are looking way down the road at what could we do with really pushing the technology boundaries and developing new concepts for new kinds of missions for exploration and science. Space technology research grants, that's grants to academic graduate students, to professors, and to other early stage innovators looking at concepts in the lower technology readiness level end of the scale. And the Center Innovation Fund taps into the NASA centers, the expertise and the innovative spirit that we can find pocketed in the different NASA centers across the country, and funds activities to develop technologies specifically coming out of the centers. And then over on the far right, we have the Centennial Challenges. These are challenge-type competitions. We're looking at everything from an interplanetary CubeSat challenge that we're developing to a Rover challenge. You see that depicted in the picture that goes with that item. Flight Opportunities is looking at putting payloads on suborbital and even orbital platforms, trying to find opportunities to get a technology into space. So it's everything from the zero-G type spacecraft or aircraft that flies the parabolas and gives you 30 seconds or so of microgravity over and over again, to sounding rockets, to high-altitude balloons. Virgin Galactic is signing up to carry some payloads. And so that's the kind of activity that goes there. Then you see the small business innovative research and the small business technology transfer. So it's a wide range of programs, each of which has a bunch of projects underneath it, and looking at all the different technology areas within NASA, contributing to NASA missions and contributing to the aerospace enterprise, and looking across the spectrum of technology readiness level. We've been thinking lately about where do we really want to go big in space technology. Got a lot of activities across a lot of areas, as I've highlighted there, but we're kind of focusing in on some specific areas of emphasis. These are areas where we'll really invest significantly. A lot of these relate to the Mars and the deep space emphasis that's you see expressed by the agency these days, but there's also space observatory systems. So you can see a range of activities: high power solar electric propulsion. We will be investing in other kinds of propulsion, but we'll be specifically targeting an investment in high power solar electric because of what that opens up for asteroid retrieval, for cargo to Mars, for all sorts of activities in space flight. Space optical communications, not only the near Earth, but the deep space. How do we get high bandwidth data back from Mars? Advanced life support and resource utilization, that's devoted to Mars and being able to set up shop and live in deep space. Entry, descent, and landing is a particular problem for Mars. We have to get there, propulsion. We have to land there, entry, descent, and landing. We have to live there, that's the life support and resource utilization. And then we want to return. That also bears on life support and resource utilization, propulsion, and other discipline areas. Robotic systems, if we're going to set up shop on Mars, we want to have crews there continually. Who's going to tend the store when the crews are gone? So that's autonomous systems development, as well as robots, humanoid and other sort of platforms that can tend the store, mind the store when crews aren't present, and can augment crew activities on a planetary body. Lightweight space structures, being able to put together, maybe even reconfigure things in space to serve multiple purposes. And deep space navigation for planetary science, and then space observatory systems. What's the next generation of great observatories going to look like? Can we do things with small platforms? Can we do things economically? So these are going to be particular areas of emphasis in space technology over the next 3 to 5 years. You'll see solicitations, you'll see investment by STMD in these areas. This is a slide we showed earlier today in another session this morning. And it kind of gives the philosophy that I talked about just a minute ago. Going there, landing there, living there, and leaving there. Coming home safely is the notion there. You can see the different technology areas, and we're actually working in space technology. Much of this is in partnership with Human Exploration and Jason's enterprise, the Advanced Exploration Systems Program. To work in each one of these areas that are highlighted on the slide. I'll show some of the results that are coming in some of these areas in the next few slides, but this kind of gives you the overview of all the infrastructure and all the technologies that underlie going to deep space, doing an asteroid mission, pointed out here on the upper left, going to Mars, setting up shop on the surface of Mars, and all the different aspects that go along with that. You see human presence, you see robotic presence, a couple of different robotic platforms. Still being determined what those things will really look like, but we know we'll need them in some implementation. I like the quote that's used there. It comes out of the National Research Council report that they issued recently on human spaceflight, the NASA activities and plans in human spaceflight. And they say developing the capabilities to land humans on Mars will not only require considerable resources, but also considerable technological innovation in many disciplines to accommodate the environments to be encountered in space during surface operations. So you can see in-space investment and surface operation investment there. So here's a long laundry list. I tried to highlight in bold letters the things that I might want you to notice, particularly here, which is just the technology areas. It gives a little information on what each of those technology areas is for, and you see it tying back to the previous slide, the entry, descent, and landing, the life support systems, the propulsion systems, the crew operation systems, and so forth. So you see a long list of things, everything from structures to propulsion to power to entry, descent, and landing technologies. You see thermal protection systems in there, deployable aeroshells, inflatable aerodynamic decelerators like Mark will talk about in much more detail, in situ resource utilization, robotics, optical communication, and other life support activities like synthetic biology membranes. There's highlighted here a few pictures. I'll give a little more detail on the solar array effort that we've had ongoing. You see that in the lower left here, trying to develop the arrays for high power solar electric propulsion. So a lot of investment in STMD focused on human exploration of Mars and asteroid retrieval. Also investing in technologies that contribute to the Space Launch System and to Orion. A little bit of effort associated with Orion, a little bit more associated with SLS, specifically the exploration upper stage. If you were at the plenary session this morning, you heard Bill Hill talk about the exploration upper stage. And what STMD is doing is working in partnership with Jason and Advanced Exploration Systems and the SLS Program Office to try to develop composite structures for the exploration upper stage. We'd like to get composite propellant tanks in there. That may come in the second version of the exploration upper stage rather than the first, although I'll show some results that we're starting to get on composite cryogenic propellant tanks for oxygen and hydrogen. But what we think we can get in the initial version of the exploration upper stage is the dry structures, skirts around the hydrogen tank, for example, struts, those sorts of things, interstage pieces. And so we're initiating a program, a project within our Technology Demonstration Missions program to develop the forward and aft skirts, true prototypes of those 8.4 meter diameter composite structures for the exploration upper stage. Coming up with manufacturing techniques for very massive composites. 8.4 meters is even larger than the largest composite structure that's on the Boeing aircraft. And so we've been doing a cryogenic propellant tank. You can see that listed on, or shown on the lower left there. And that's 5.5 meters. That was done with an out of autoclave manufacturing process. For the skirts on exploration upper stage, we might do those in segments and use autoclave. That's still part of the formulation effort to determine how we'll do that exactly. But making very large structures can reduce the mass and maybe allow for more payload on the upper stage. I mentioned the composite cryogenic propellant tanks. We made a 2.4 meter Pathfinder, put oxygen in that. That worked real well. We made a 5.5 meter tank that we took then down to Marshall Space Flight Center. Boeing actually manufactured the tank, and it's being tested right now, ultimately to hold hydrogen. I'll show some initial results from the structural load testing of that tank and the thermal testing. Cryogenic propellant storage, architectures for sending humans to Mars and returning humans to Mars may end up relying on being able to store hydrogen, hard cryo, or oxygen and methane, soft cryos, for long periods of time, months, maybe more than a year. And so, or staging them, say, in Mars orbits for return back to Earth. And so we have been working in STMD on methods of storing cryogenic propellant for long periods of time, technologies, insulation technologies, and other heat rejection and methods of dealing with the thermal loads on cryogenic propellants. Additive manufacturing is something that's taking the nation by storm, taking the world by storm, really, and it's being applied to rocket engines. Several companies and NASA centers are engaged in looking at what components can we make. Could we even make, for small engines, the whole engine out of additive manufacturing? So there's a lot of work in that activity, and STMD is working on some of that. You can see a few things here for Orion, some very specific applications where we might be able to improve some of the issues with, and mitigate some of the issues that Orion is seeing as it tries to get its spacecraft ready for the first few flights. Then lastly, outer planetary exploration. A big focus for us has been the Discovery 2014 call for proposals that's been put out by Science Mission Directorate. In that call, there's several technologies listed from Advanced Exploration Systems and Space Technology Mission Directorate that NASA would provide if the proposers, wish to use them. So you see some of them listed there. deep space optical comm, the deep space atomic clock. And then there's some other technologies there that we're working on. We're either continuing these projects or initiating efforts in FY15 to work in these areas that support outer planetary exploration. So it'll be interesting to see late this year when the Discovery 2014 proposals come in and the selection ultimately gets made, whether they're what advanced technologies are going to be used on that mission. So, I kind of teased it earlier. The data is coming in. We're getting some results. Well, the fruits of our investments are being harvested. And so here's the first one: high power solar arrays. You can see two different concepts here. We developed two concepts, two TRL between 5 and 6. Really, we'll call it 5 plus. I think that's what it says on the slide there. There's a circular concept that's from ATK, Lion Technical Systems, Lion Tech Systems. It builds on the Orion type array. It's larger. These are about 20 kilowatts per wing, roughly. So that wing there, that would be one wing in the parlance, and that's 18 to 20 kilowatts depending on the efficiency of the solar cells you populate it with. I was at the demonstration for that one snowy day. It was actually kind of a blizzard in Cleveland, near Cleveland at the Plumbrook station, and it was just a fabulous demonstration of flawless, very, very quick deployment of the array from a very small wedge all the way out and around. And then on the right you see the rollout solar array, or ROSA. Different means of deploying the solar array where it's literally rolled up and unrolled to deploy. You can kind of see the roller there on the bottom of the images there on the lower right. This is from Deployable Space Systems. Both of these companies do this work out in Goleta, California. And so they did a very excellent, flawless deployment of their array a little bit later in the spring than ATK deployed theirs. And so we've got two concepts here that are available. Perhaps both will be implemented in different sorts of applications. But these are really ready to take to the next step to a spaceflight demonstration. Really with these, the development has been done. We're ready for demonstration. They might be demonstrated on the asteroid return mission, but space technology is committed to doing a high power solar electric propulsion demonstration in conjunction with the asteroid mission if that ends up going forward. But if it doesn't, we'll do a demonstration in any case. So in addition to the arrays, we're also working on high power thrusters, specifically a 12.5 kilowatt Hall thruster. There are other possibilities from industry for high power Hall thrusters as well. And then the power processing units that go along with them. People sometimes tend to not emphasize the power processing. That's just electronics, right? But I know a guy who's worked in this business for many years who says that thrusters are easy and PPUs can break your heart. And so we are trying to spend a lot of effort on the power processing equipment as well. Here's the Supersonic Decelerator. I'll just show the glimpse of this. Mark will give you much more detail, but we're all just delighted that about 5 weeks ago we were able to fly this, and that we'd have been happy if we'd have just got the test vehicle to the appropriate test conditions. That was really the goal of the first shakeout flight, because we had to develop a whole infrastructure for actually conducting the test, getting these devices to the right environment to conduct the test, to simulate entry into Mars. It involved high altitude balloons and kind of an exotic launch stand apparatus, and and hanging a big solid rocket off a balloon and floating it out over the ocean. And so Mark will give you a lot of detail on that, but we exceeded we met every one of the test objectives, and we exceeded them by a long shot. The test wasn't perfect, and we're learning, we've got a lot of learning to do about one specific element of the test, but anyway, this was a fabulous success for STMD, and we're really, really excited to hear Mark's details on that. Here's the cryogenic propellant tank. So this is all composite. The 5.5 meter tank was flown from Boeing to Marshall in the Super Guppy, which is a cool looking aircraft. It actually does look like a fish, sort of. And so the tank has been pressurized just a couple of weeks ago to about 60 psi at cryogenic conditions. And the deformation is 5,000 microstrain. That's a measurement of deformation. The test objective was achieved, and the tank held up to that. So there'll be more tests continuing with this tank over the remaining months of the summer. But first results suggest that this tank will hold up to cryogenic temperatures and the loads that it would be subjected to in use in an upper stage. And so being able to replace a metal propellant tank with a composite propellant tank might save as much as 20% or so on the mass. The dry structures we're developing, the composite dry structures, we're looking at trying to decrease the thermal loads on the tank as well. And so a lot of efforts devoted to storing and maintaining cryogenic propellants as efficiently as we can, trying to increase the throw mass of an exploration upper stage, or the payload mass. I always tell people that in rocketry, it's the dirty little secret is the payload is an embarrassingly small fraction of the rocket. But we do the best we can do, and we try to develop technologies to improve on that when we can. We have this thing called a green propellant. It's not actually green. That's the lasers that are being used to interrogate the plume of the propellant that's green. It's green in the sense of environmental friendliness. Now, propellants are energetic materials, otherwise they wouldn't be propellants, so I wouldn't recommend that you drink the fancy new green propellant. But it is a lot less hazardous than hydrazine. Its environmental impact is much lower. If we spill it on the ground, we just wipe it up with rags. We can handle it without getting in a self-controlled breathing apparatus suit. So it's a very low toxicity. It's got a very low vapor pressure, which is why you don't have to wear the escape suit. And better yet, it's got 50% higher density than hydrazine, and it's got about 20 seconds greater specific impulse as a monopropellant than hydrazine. So it's higher performing, higher density, and easier to handle and store. And so we've been developing, as you can see in the upper right, a spacecraft. Kind of reminds me of the flying toaster that used to be popular in the first ever screensavers, for the older members of the audience. But our flying toaster spacecraft, it looks like a flying dishwasher or something maybe. But it's a Ball spacecraft bus, an aerojet propulsion technology put together. And we're going to fly this demonstration early 2016. It'll have attitude control and primary propulsion. Attitude control through 1 Newton thrusters, primary propulsion through a single 22 Newton thruster. So we'll demonstrate attitude control, orbit changing with this spacecraft, and get this green propulsion system, the valves, the tanks, the bladder materials you have to use in the tanks, well, the whole system to a point where it can be infused into missions. There's a lot of excitement in industry for this kind of propulsion system and getting away from the use of hydrazine and using something that has a higher volumetric impulse. So where are we on this? We've fired the 1 Newton thruster. Aerojet has developed that, put it in the thrust stand, fired it. This is an engineering model, so it's full flight-like design. And put 11,000 pulses on that, ran it for many cumulative hours, and so that looks ready to go. 22 Newton thruster is next. Hot fire testing should start on August 19th, according to the current schedule, so that's maybe 2 weeks from yesterday or Tuesday. So making a lot of progress on that. Really excited about this demonstration. We will actually launch this on a DoD flight, STP, the Space Test Program, their STP-2 launch, which is a SpaceX rocket, will have this demonstration, and it will have our deep space atomic clock demonstration as well. So we're getting a twofer on that one, which will be really, really exciting. And we'll have our fingers crossed, of course. Mars 2020 rover, we talked about this a little bit earlier in the morning. This is a really exciting partnership that we're doing with Human Exploration and Operations. STMD and HEOMD are jointly putting up the resources for this demonstration. So this selection was announced last week. The specific item is the thing that you see in the lower middle called Mach. There are lots of other instruments on the rover, a full science payload to do all sorts of optical measurements, to do some very precise characterization of the dust on Mars. But the Mach, the Mars Oxygen In Situ Resource Experiment, is designed to suck the Mars atmosphere in, which is mostly CO2, a little bit of nitrogen, a little bit of argon, a few traces of other things, but it's about 96% CO2, and filter it, get the dust out, pump out the residual nitrogen and oxygen, nitrogen and argon, and then send the CO2 to a solid oxide electrolysis unit where it's converted into oxygen. So the call for proposals specified certain flow rate of oxygen that you needed to get, a certain duration of the experiment, and we reviewed several proposals that addressed all those issues, and finally ultimately selected this one. It's a partnership between MIT, JPL, Ceramatech, who's providing the solid oxide electrolysis system, and Cryogenic, that's providing some cryogenic pumping capability. You can see the packaging on the lower left there. The size of it, 9.3 kilograms, about 20 pounds. And the volume, the dimensions there, I tried to find a rough equivalence, and I came up with about 1.5 standard men's shoe boxes. So bigger than a bread box maybe, but not much. And so this will produce 20 grams an hour of oxygen with 99.6 purity. And you can see the other objectives there. Operate for 50 sols over a duration of 50 sols on Mars days. That's what a sol is. Demonstrate resilience with respect to dust and other environmental challenges, and return knowledge, this is really important actually, return knowledge of critical performance parameters that can be used in scaling it up to ultimately human class exploration system. And one of the elements of the call for proposals was you got to propose something that can be scaled up ultimately. And so I've listed there how it works, just by sucking in the atmosphere, storing the CO2, and then at any later time you desire, flowing that into the solid oxide electrolysis unit and converting it to oxygen. There's some diagnostics there to characterize the purity of that oxygen. So those are some highlights of what space technology is doing. Hope I haven't stolen time from my colleagues here. Right now, NASA is engaged in a technology emphasis, and so there's information being tweeted out every day. All the interesting activities, not only in STMD, but other NASA technology activities in ARMD and AES are being publicized. So you can follow the tweets there at 321 TechOff, and you can go to nasa.gov Space Tech for more information. So appreciate the opportunity to talk to you. Thanks for your attention. I'll turn it over to Mark Adler here.
Good afternoon. I'm going to talk about the low-density supersonic decelerator project as one of the many projects that Jeff just talked about. I'll try and keep it a little shorter than Jeff's talk. So let's see here. Okay, so this project is to develop decelerators for Mars landing vehicles. These, and it's called low density, not referring to the decelerators, but referring to the Mars atmosphere. It's the one atmosphere of a destination that we try to go to that has a very low density atmosphere, and that's really annoying to designers of entry vehicles because there's not enough stuff there to try and slow down your vehicle. So we have to slow things down at very high speeds, hence they have to be supersonic. So the purpose of this is to try and enable larger payloads to Mars. You see up here actually some testing that was done in the 70s. It was actually in the summer of 1972, about 42 years ago. A test actually somewhat similar to the one that we just did 5 weeks ago, where they tested a parachute for the Viking lander at Mars. And today we still use the data from that test 42 years ago to qualify our supersonic parachutes at Mars. We haven't done this test since then until a few weeks ago to try and understand how parachutes work supersonically. We have exceeded the value of this test. We've exceeded the kind of qualifications that this test has done when we go to larger payloads on Mars. On the corner here, you can see we've been going from a Sojourner rover, a little tiny microwave-sized rover, to Mars Exploration Rover, about the size of a little golf cart, to Phoenix Mars lander, still bigger, to our Mini Cooper-sized Mars Science Laboratory on Mars. We want to go bigger still. Someday we want to put humans on Mars in little two-story condominiums or whatever it is we want to put down to get them on the surface, to have them live there, and to get them back off the surface in Mars ascent vehicles. So we have to make this step from small things to bigger and bigger and bigger things. Unfortunately, we are the victim in this case of a square cube law problem, where as our vehicles get larger in size, they go up in mass as the cube of the size, but they go up in area only as the square of the size. And so that drag area is not growing as quickly as the mass. And so you end up with these vehicles coming in with much higher ballistic coefficients, and they end up going even faster and faster before you need to start deploying decelerators to slow them down. These vehicles will hit the ground supersonically if you don't deploy something to slow them down. And that something is what we're working on. So here are three of the somethings. These are the three technologies we're developing. This is called a SIAD, a Supersonic Inflatable Aerodynamic Decelerator. It deploys at about Mach 4. And it increases the size of the vehicle from about 4.5 meters to 6 meters, and then provides about 2 times the drag area to slow the vehicle down at very high Mach. The higher the Mach we can slow down, the better off we are to get to the conditions we need to be at before we can start firing the rockets to actually land the vehicle. This is a larger SIAD that we're developing. In fact, Ben Tutt's in the audience working on this one here from Airborne. This is the SIAD-E. It is a larger, more efficient SIAD. This one is similar in mass to this one, but it'll go up to about 8 meters. The one over here, the SIAD-E, the SIAD-R, the smaller one, is inflated entirely by gas provided by the vehicle. This one just gets started by gas provided by the vehicle, but then has ram air inlets here that allow it to take in air from the airstream and keep it inflated, so it's able to make use of that air to be lighter, but it's a little bit more complicated, a little bit more risky to try and get working. And we're developing a very large parachute. Mars Science Laboratory in 2012 landed on Mars with a 21.5 meter supersonic parachute, even larger than the largest parachute that was ever flown back in the 60s and 70s for the testing, so we were kind of pushing the limits here. But we're developing a 30.5 meter parachute, much larger than the 21.5 to land much larger payloads. And you'll see more about that. This was part of a test we were doing to test the payload out at China Lake, where we do rocket sled testing to get the strength testing on these rockets. On these decelerators using rockets. In fact, this is examples of these tests. This rocket sled facility in China Lake is really great. It's a 4-mile long railroad track, a very straight, very precise railroad track on which we put these rocket sleds. The rocket sleds are just steel shoes that grab the track. There's no wheels, there's no grease. You just put big rockets on here and it goes. And these things go up to about 300 miles an hour to test this here. And we also have another one where we actually pull a rope through a pulley to get the parachute. This is pretty much the configuration here. A parachute up here, rockets and pulley down here. So they pull the parachute down with 100,000 pounds of force to test the parachute and the loads that it would experience at Mars. But the real test, and the hardest test, as Jeff mentioned, is to get these things to actual condition that they would see at Mars. To do that, to get to the low densities we have at Mars, you have to go very, very high in the Earth's atmosphere. We have to go up to about 180, 190,000 feet in Earth's atmosphere, in our stratosphere, in the top of the stratosphere, to get to the Mars densities. And we have to get a full-size vehicle up there. We can't do subscale testing on these things. The only way to know if they're going to work is to do full-scale testing. We can't scale the devices. We can't simulate the scaling. So we have to do full-scale devices, full-scale entry vehicles at the high altitudes to get the low density and at the speed. So we have to get up to Mach 4 at 190,000 feet with a full-scale 7,000-pound vehicle to test the vehicles, to test the supersonic inflatable decelerator, and then as it slows down to test the parachute, and then eventually to come back down. So the way we do this is we actually launch out of the Pacific Missile Range facility in Kaua'i, on the west end of Kaua'i, and we go out over the Pacific Ocean. The balloon, a large scientific balloon, a 34 million cubic foot balloon, takes us out over the ocean, takes us up to about 120,000 feet, which gets us partway there. And then it drops the vehicle. We then fire the engine, a large Star 48 rocket motor, the same as used in many of our third stages of our launch vehicles, to get us up to 190,000 feet in Mach 4, where we deploy these things going roughly horizontally, so we get a long test time at the proper density, deploy the decelerator and the parachute, and then come down, eventually impact the water where we recover the vehicle. So now, we were showing this view graph for a couple of years. We actually did it about 5 weeks ago. So on June 28th, we after several weeks of trying to get good weather conditions to do this, we had the thing set up in the early morning. This is showing just before sunset. We dropped the vehicle, fired it, deployed the side, deployed the parachute. I'll show you some videos of all of this. So starting with the launch, this is the balloon set up. The balloon actually goes all the way out to here, so you see this little red parachute here. This is all balloon material. On the ground, only a little bubble at the top of the balloon is filled up. Once it gets up to altitude, the whole balloon fills up. It could fill up the Rose Bowl. So this is the balloon being released. This is the helium going up, helium balloon going up on the top part of the balloon. This little collar will be released, which allows the helium to go into the rest of the balloon eventually. This keeping the helium up here allows for a more controlled launch. This whole apparatus was provided by the Columbia Scientific Balloon Facility. These are great folk that work out of Palestine, Texas, that do these launches all the time for astrophysics payloads. And so, but we had to adapt the system considerably to allow a launch of a solid rocket motor safely. And so we had to develop this tower that the vehicle is hanging on. Here we see it coming up over the tower. Here's the guys operating it from Columbia Scientific Balloon Facility. And there's our vehicle, our test vehicle with the solid rocket motor looking up, and boop, off it comes to the tower and launches going up at about 1,100, 1,200 feet per minute very quickly into the air. There's our little launch team, very happy about this finally. Then it took about 2.5 hours for this thing to get up to altitude and float out over the Pacific to a safe area where we can conduct the test. Past a little island just west of Kauai called Ni'ihau. And once we were able to get out, got to altitude, got to float altitude, we were able to drop the vehicle. So we drop the vehicle, it spins up. There's 2 sets of spin motors that fire, and then this large Star 48 rocket motor fires. See the Earth spinning in the background. It's going about 50 RPM. The Star 48 motor fires for about 71 seconds, and got it from Mach 0 to Mach 4.3 in a little over a minute, and got it from 120,000 feet to 191,000 feet in that same time, going roughly horizontally. This vehicle, when it was dropped from the balloon, weighed about 7,000 pounds. By the time the rocket motor finished firing, it was about 3,000 pounds. Most of it, a lot of rocket propellant in there to try and get it up to speed. This picture was taken by a GoPro camera. We used actually several GoPro cameras. We had a lot of commercial devices on this to try and make it low cost.
It's good advertisement for GoPro.
Yeah, well, I think GoPro is going to see this tomorrow for the first time. We're going to have a press conference tomorrow morning, and we're going to be releasing a lot of these videos for the first time, so you're getting a preview of that. And then the other set of spin motors fired, stopped the vehicle very well, despun it really well, and we showed very stable flight after that. So we got up to Mach 4.3, so that was the first thing we really wanted out of this test. Really the main thing we wanted out of this test was to show that we could get this vehicle to altitude, we could launch out of PMRS safely. That was a whole ordeal in itself I could tell you about. And be able to get it to altitude and get to speed so that we can get these devices to the conditions that they will see at Mars. And that was successful. So that was what Jeff was talking about when he said this mission was a complete success. By the time we got to this, there was the complete success. We got to the condition, so we showed what we can do for getting these devices to condition, which is exactly what we're going to do next summer. So we have 2 more flights planned for next summer. We're going to really test the technologies. But we had technologies on here anyway because we wanted to make use of the flight. And so there you see deployment of the SIAD-R. That's the 6-meter side that deployed very rapidly using the actually automotive airbag gas generators that we used aboard again to reduce cost. And you'll see another view of this. You see that one of the things we wanted to see is that it deployed quickly and properly, that it didn't introduce any vehicle dynamics, and it didn't. The vehicle, in fact, became a little bit more stable once this thing was deployed. It was very rigid. We had measurements of the rigidity of the SIAD-R to show that it would not flex very much. Here's another view of the same deployment. And that rigidity is important for extensibility of the SIAD-R to other applications without having to do further supersonic tests. So here is the supersonic deployment of the parachute. So the first thing we deploy is this balloon. It's actually a 4.4 meter balloon. This is used, a pilot balloon, to pull the parachute out. So now that thing pulls the parachute out. Oh boy. You can see here, so the parachute pretty much had a very rapid, unplanned disassembly in its deployment. That was one of the reasons we wanted to do the test. And oddly, we're very happy to see this failure because we would have much rather seen this failure this year than next year. Next year would have been a big impact on our cost and schedule. But since we were able to get the parachute on this flight, which was sort of a bonus opportunity, we weren't required to do that, but we got it on precisely for this reason because I wanted to see if this thing would work or not. And we got some very excellent video. In fact, I'll show you a little bit of the video of the parachute. Here's our high-speed camera. This is about factor of 10 slower than real time. Getting some very high-resolution images. Here you see the balloon being deployed. And the balloon worked fantastically. This is one of the other things we were worried about. We wanted to show that the balloon would also work and be able to get the parachute out, and it worked fantastically. So the drag on this thing is what's used to pull the parachute out of the vehicle and get it out into the flow for deployment. So in a second we'll see that. And this is we also had another camera. We had this was our high-speed camera. We also had a high-resolution camera at a lower frame, which gives us even higher resolution pictures. We're going to be releasing some of that stuff in the press conference tomorrow. So once this thing is stable, the bridles on the back here are released right now, and out comes the balloon pulling out the parachute from the container, and you'll see here are the bridles for the parachute. And there's the shroud lines coming out of the parachute bag, so we see the parachute being deployed. And the balloon is now disconnected from the parachute. The bag has come off completely. The parachute opens up. It actually opened up pretty well, but before it could even get deployed, there were several rips in the parachute, and from there on, in the supersonic flow, the parachute was destroyed by the flow. And so we learned actually a great deal from this failure. We've seen phenomenon we had never seen before, and in fact, because we had such great video, the high-speed, high-resolution videos that we got back from the vehicle. We are now observing phenomenon that we had never noticed before in the old stuff that we had from the 70s. And so we have these old films from the 70s, and we're now looking back at them and going, oh, look, that's what was happening there, now that we have this high-resolution stuff to see what was really happening. So we discovered new failure modes. Of course, we now understand what happened to the parachute. We're now redesigning the parachute for the next flights that we're going to have next year. So after this thing came down, it came down in the water pretty hard, but we were able to recover a lot of stuff. This is the balloon in the water, so we had our recovery boats go out, and we actually were lucky to find the balloon and bring that back. Here's the test vehicle itself in the water. It was actually designed to float. This is our supersonic space boat, and so this actually the core structure is built into it a foam which is buoyant even if the thing completely fills with water, so that we can recover. So there's the spent Star 48 motor sticking out. This is our camera mast where all the fantastic cameras were that filmed the events. And this is the SIAD now deflated, sticking around the side right here. This is two EOD guys. This is our explosive ordnance disposal guys. They're divers from the Navy. And they're sitting on the boat. If you ask me afterwards, I'll tell you what they were talking about while they were sitting there. Because on their heads are these GoPro cameras. We wanted them to document the state of the vehicle before we banged it into the side of the boat while recovering it. And so they got good documentation with the GoPro cameras of the video, but they also have audio, so we heard what they were saying. And so this was actually floating in the water for a while. They got to our space boat first on a small fast boat. They were waiting for the large boat with the crane to come by to get it. So they're just out here waiting for the big boat to get there. And once the big boat got there, It had the crane. We pulled the vehicle up out of the water and got onto the boat, brought it back to the dock, and we completely disassembled the vehicle once it got back to the assembly building at the Pacific Missile Range Facility. Recovered all the camera video, which we didn't telemeter down. Recovered all the equipment, the SIAD, and also we brought back in the parachute, see what was left of the parachute. Got that out of the water, brought that back in, so we were able to examine the parachute as well and understand exactly what happened to it and where it happened to it. So it was incredibly valuable to get that back as well. So that's the testing that we did this summer. We did a shakeout of the vehicle. The vehicle worked perfectly to get the technologies to where they wanted to be. We also got to test 2 technologies, and we got to see a failure on one of them so that we can address that and have a much better chance of having successful flights next year. And this is, as a preview, this is our first core structure coming back for one of our 2 vehicles next year. This is already in our high bay at JPL, so we're going to start integration soon for the second vehicle, and then the third core structure is going to be coming in a couple of weeks, and so we're going to start building up those 2 vehicles. On those, we're going to have 2 more SIADs and 2 more parachutes with a new design. And those are the runs for the record. Those are the tests where we want to take the technologies and bring them up to TRL-6 and show that they're ready for adoption by a flight project. So that's it, and we'll be on the panel. I'll be able to answer some questions later. Thank you.
Okay, so I'm Jason Kersan. I was on the Planetary this morning talking a little bit about our architecture type work that we've been doing and a couple of highlights within AES. But what I'm going to do is walk you through a little bit more potentially on the architecture side, but then a summary version of a lot of the AES portfolio. The more detailed versions of a lot of our projects actually are in various sessions, and a lot of our project managers are here, so if you have interest in those, hopefully you caught their sessions already, or we'll catch the remaining sessions this afternoon. This morning I talked about the 6 principles related to our exploration implementation. I won't walk through them today, but these are, when we're looking at what technology investments we do, even on our technology risk reduction activities and capability advancements, we are guided by these at the very beginning. As we move from this Earth-reliant to Earth-independent phase, we're looking at where are the commonalities of capabilities, and how do we boil those down to technology advancements and system advancement that need to be made over this whole plethora from here to all the way to the surface of Mars. This morning I talked about a lot of the trade studies going on in our Valuable Mars campaigns, some things that we're revisiting like SEP that we've heard about, ISRU, some of the robotic precursors activities. What kind of precursors do we need to know to do measurements before we send folks? Where are the partnership opportunities with our international partners and our science mission directorate colleagues on some of those robotic precursors that we can go after? I also talked about this morning about how then it drives our overall difference in the way we evaluate and look at our overall campaign structure that we have. So AES was started about 3 years ago, at the same time actually as the Space Technology Program was stood up under OCT, the predecessor to the Mission Directorate. And AES was stood up to advance overall systems level development and operational concepts for future human spaceflight. It's set up as a very hands-on organization, doing ground tests, field tests, tests on station, and increasingly even flight experiments as a robotic activity. We also rely heavily on a civil servant workforce. So we have about 600 folks that work in AES across all the NASA centers. That is a cautionary note for us, though. Because of that large internal working group we have, we try to go above and beyond on trying to develop new public-private partnerships, maximizing contracts through SBIR and other mechanisms like that to balance that internal workforce that we have. And then we, of course, partner with our space tech and science colleagues on a number of different areas, and I'll try to point out some of them. This is just a vanity shot of the different types of systems, from habitat up in the top to concepts that we're looking for advanced augmentation modules, some of the first habitation requirements that we'll need. A lot of the spacesuit work that you've seen as part of our ARM missions, we're developing the potential concepts for the modified ascent-descent suit. Work there, and then we're actually still working on the exploration suit garments and such that you see down there with the Z2 suit there. I also note in the bottom right-hand corner, advancing state-of-the-art in guidance, navigation, and control, and test bed facilities like spheres on board the space station. And that's also helping us lead to some of our smaller class missions. We have a whole series of 6U CubeSats that are slated to be flying on EM1. 2 of them are utilizing solar sails, and I believe some of those were talked about here and also at the SmallSat conference this week. So to dive into a couple of these different domain areas, we kind of group things and manage them by domains and disciplines. So the first one is crew mobility. So we're advancing a lot of the EVA suit from the garment side to the portable life support system to the modified ascent and descent suit that's going on in the neutral buoyancy lab with us and our Orion colleagues that they're advancing. The PLIS made a huge set of milestones this year. This is the first primary life support system that's been designed at NASA in over 30 years. And it is up and operational and in a test environment as we speak. That's what you see on the left-hand side is the real unit along with a simulant for crew load over there in the mock-up of the glassy garment there. And then you're seeing the modified ASIS and kind of how we would attach this primary life support system to an ascent and descent suit to give us limited EVA capabilities in the near term on things like R. But just designing the engineering isn't enough. Actually getting in the tank and actually running a whole series of neutral buoyancy lab tests. So we've been working closely with Orion. They've been doing their standard ingress and egress routines that they would be doing for Orion for a lot of their situations. We've piggybacked on those tests and then added in a whole set of test objectives related to how we would traverse the asteroid vehicle, redirect vehicle, and then actually manipulate and take samples off of an asteroid itself. And that's been a whole series of tests over the past several months here. And you can see down at the bottom of how we are actually working on how to do weight balancing, CG management in this way, all the way to the tools and even most recently some of the PLIS mock-up and looking at that as far as overall impacts of the suit and the crew movement. Deep space habitat. So we got a number of efforts related to habitat type work. First off is exploration augmentation module. We're now looking at what are the first steps that it takes to augment Orion from a habitation perspective to allow it to go from its 20 to 30 day class missions up to longer duration missions. And this is really what are the first building blocks to our Mars transit hab? And how do we modularize that into an initial capability, an augmentation module, and then scale it into the Mars class habitation that we need? So that's what our EAM folks are doing. A Bigelow expandable activity module. This is a cost-sharing public-private partnership with Bigelow as a commercial company. And we're looking at the advancement of technologies for thermal control and radiation performance of soft goods, plus certifying the first soft goods structure on the space station that we've flown to date. We have a whole plethora of ECLIS, environmental life support type work. Today we separate that into our atmospheric recovery. And what you see there is an image of the simulation facility that we can simulate the entire environment on station, including all the loads and the metabolic loads and that. And we can actually then do incremental improvements on the life support system that we have on station and test out those advancements in that chamber real time before we go to take those to flight. In addition to that, we're looking at different water recovery mechanisms. We're at about 85% closed loop if everything on station is running today, and we're trying to get that last 15%. That involves things like recovering the brine and some other very difficult water recovery efforts, but we're starting the investments in that last 15%. Down on the bottom left-hand side is radiation protection. So we have a radiation protection effort, but it's mainly actually on the sensor work. So we've been developing a whole series of radiation sensors that are actually slated to fly on every human vehicle that we have in our fleet and plan to have in our fleet. Today, we were the ones that funded the RAD instrument that's on Curiosity, led by those folks. And then the same kind of derivative instrument is being built for station, but at the same time, we have another instrument that's called Metapix. It's a very small, lightweight radiation sensor that we have on station today. And what you see in the little images here are actually the radiation sensors, the pair of them, that will be flying on EFT-1 that have already been delivered. And then we're slating then to follow on from EFT-1 to the actual radiation sensors that'll be on EM-1, and those will be the baseline sensors that will be for Orion for all of our monitoring. Logistics reduction, we're looking at a number of aspects in logistics reduction, from advanced clothing, long wear clothing that's getting ready to go up on station SpaceX 4, right, Jim? It's there now, okay. Getting ready to start to be used, I guess is the way I should say. But from that type of work to heat melt compactors, compacting our trash into useful or just reduce the volume or sterilize the biologicals in it, to looking at next generation waste management systems and the like that. Additive manufacturing, so in space manufacturing, there's been a lot of talk about 3D printers. There is a 3D printer going on SpaceX 4. It was jointly funded between the ISS, STMD, and AES, and we're really excited to see that go fly coming up on SpaceX 4. And that is a precursor to an actual additive manufacturing facility that we intend to put on station as a permanent express rack locker facility there to look at future concepts. Spacecraft fire safety. This is really neat because we're actually going to start a large-scale fire on a Cygnus vehicle before it re-enters, which will be fun. So what you're looking at there is the engineering drawing, although we actually have the hardware in near done state for the first unit at this point. And the test chamber there is about 1 meter by 1/2 meter in size. To date, the largest scale burning demonstrations we've done on station is about the size of a Post-it note. So this is going to be significantly larger, looking at large-scale flame propagation and what are its effects, and does it actually propagate? There's a lot of discussion about that. So the first test will be a large sample by 1 meter by 1/2 meter, and the next test after that will be 9 different materials tests laid out. And then the third sample card will probably go back to a large sample again. But we're intending to fly this over 3 different orbital Cygnus flights, and it'll be activated after the crew closes the door, and we'll back away. We'll run the test and take about 7 to 8 days to downlink all the scientific data and video data. So we're looking forward to that. On the Bigelow module, we're on track to deliver, Bigelow's on track to deliver in January of next year. You'll note that that is 24 months from contract signature. So 24 months from contract signature to delivery date on dock, ready to go fly. So we're really about trying to get things done in a very rapid and efficient way. This will be 18 cubic meters of volume, and it'll be going on node 3 aft for those that are looking at the image there. Vehicle systems. John O'Lanson gave a presentation on Morpheus, so I won't go into a lot of detail on that. We've been obviously using it for a multitude of reasons. Morpheus has been a great in-house development effort of actually doing lander technology advancement and rebuilding our capabilities in that area as an agency. But at the same time, we've been testing some critical hazard avoidance technology, all HAT, on that platform and looking at closed-loop autonomous control and hazard avoidance and recalculation of navigation algorithms for those tests. We culminated for our 14th free flight earlier this year, finalizing in a night flight, which was part of our test characteristics to be able to fly in all lighting conditions. So we're looking at the path forward on how do we test that vehicle, do we need to advance all HAT technology a little bit more. So there may be more to come on Morpheus, and we'll see how that goes. At the same time, this has helped us advance our landing capability, and we're also noticing what's coming in the commercial world. And we formulated an effort called Lunar Catalyst, and I'll let Nantel talk about it, but basically what we want to do is advance commercial landing capabilities and help them achieve their goal of commercial landings on the moon. So a lot of our in-house capabilities are being provided at no cost to the 3 entities, and Nantel will cover that. Modular power, everything from battery power systems for EVA to the power systems that we need for something like an exploration augmentation module, to how do we utilize some of the fuel cell technology that STMD is developing. And we're looking at integrated power architectures and fault detections and such like that under our modular power systems folks. We are doing investments in nuclear cryogenic propulsion. Our current technology investments are for nuclear thermal, and they are centered around recovering the ability to create fuel rods and driving to a fuel down select by next year. So what you see there is actually a subscale test article down at Marshall Space Flight Center, and we're working really closely with the DOE to start recovering that nuclear thermal propulsion element production capability that that the country lost after NERVA. We're also doing some work with fiber optic sensors, adapting some aircraft fiber optic sensors to launch vehicles to increase data rates with our Dryden folks and a couple other commercial entities out there. This is just a vanity shot of the Morpheus folks. I did throw in a Morpheus video. We'll see if it plays, and if not, I'm sure Alanson showed some video the other day. Yeah, I'm not seeing it, so we'll just go ahead and skip it. In the operations domain, a couple different things there. Autonomous mission operations. We're advancing basically advanced caution and warning systems and other autonomous systems to try to decrease the reliance on the crew on the ground, all of our folks on the ground. And in fact, for EFT1, we will actually take an entire telemetry stream from EFT1, pipe it into our advanced caution and warning systems, and figure out what the computers would have done, not just our operators at mission control, and see if they would have detected all the faults and such in our advanced caution and warning system. Core flight software. So there is originated Goddard effort for core flight software that's a kind of a government-owned open source software. We've been taking and building upon that, which was primarily built for robotic missions, and advancing it for human certifications, and in fact, porting core flight software so that it can actually be on human-rated systems in a very rapid way. At the core of our EVA developments and Morpheus, and our augmentation module, habitations and such, they're all running core flight software. So we see that as a critical element of how we get some commonality between all of our flight software systems across all of human spaceflight. Integrated ground operations. This is looking at automated cryogenic propellant loading down at Kennedy, and looking at next generation loading technologies that would enable us to reduce the size of our cryogenic propulsion engineers on the ground. Today, for loading of cryos, we rely on some very smart people. That's how we load cryos safely. And there's a lot of them, and they're constantly monitoring all of our cryogenic loading systems. We want to be able to introduce a lot more caution and automation in those systems in the future. And we are doing full-scale, subscale testing down at Kennedy to look at those automated systems. Avionics is looking at common avionics architectures across all this. We have been testing various different avionics architectures for human spaceflight. We've been advancing networking protocols through delay-tolerant networking and disruption-tolerant networking. And in fact, we've been doing a lot of that, and I think I have a slide on it after this, using crowdsourcing and opening up our disruptive-tolerant networking protocol development to the public at large around the world. Ka-band optical observation and monitoring, kaboom. The comm guys think it's funny, but it's looking at next generation arraying technology. So how do you array smaller commodity-style dishes for the purpose of radar? So we have 3 dishes down at Kennedy, and bringing them up to do an X-band re-verification of a test we did a year or so ago. And then after we advance through X-band, then we'll do phase arraying of Ka-band. And this is full closed-loop control arraying. So it gives us orders of magnitude more ability to use low-cost dishes for future arrays for searching like things such as near-Earth asteroids. I talked about DTN. It's interesting. We started doing a lot of the core DTN development in-house, and in fact, there's actually an open-source version of DTN out there called Ion that's available for the public. But if you know about networking protocols, there's a lot more than just the base protocol that's evolved. You have to have a lot of your assurance and security and key exchange and all that. And we're developing a lot of that through open source software and crowd-sourced development. Disruptive tolerant networking, to give you in a nutshell, is if you think of TCP/IP, the way it works today, is you have to have an acknowledgement from where you're sending to where you're receiving and the entire chain in between and all the steps there. What DTN does is enable what they call a bundle protocol that sits on top of TCP/IP and allows you just to acknowledge from one step to the next. So and then the protocol takes over in getting the best route back to where it's going to be. That's very highly advantageous to us because today we can't use TCP/IP just because of the long latency we have in a lot of our connections back from spacecraft to Earth. So if you're of the type, there's actually been a whole series of challenges out there that we've been actually offering prize money and software development money through our platform that we call NASA Tournament Lab. Robotics precursor. So I touched on the one down at the bottom left-hand side, the RAD detector that's on Curiosity today. Up through about the middle of this year, we were also the ones jointly funding with our science mission director colleagues, the Goldstone radar. So radar imaging of near-Earth asteroids after they've been optically found. Then we look at doing the full characterization with radar at Goldstone. Mars 2020, Jeff talked about Medley 2, along with our Meta and Mach experiments that will be on there. We have up in the top right-hand corner an effort called SURVEY. So there was a predecessor to this called the NASA Lunar Science Institute. It's a virtual institute. It's a research and analysis type effort. It was originally centered around the lunar as the only focus. SURVEY was expanded to be basically any atmosphereless body. So basically near-Earth asteroids, the moon, and the Mars moons. And now we're looking at interdisciplinary science and exploration analysis that fits around any airless body like that, and looking at fundamental things like lighting characteristics and regolith propagation and impact craters and that whole level of science. We have 3 EM1 secondaries. They're all 6U CubeSats. One of them is called BioSentinel. It'll be the first biological experiment sent into space since the Apollo program. And it will go out and measure the effects and differentiate the effects of radiation versus microgravity on biological organisms. I encourage you to take a look at that one. Another one's called Lunar Flashlight, which will use a solar cell to position itself in a low lunar orbit. It'll be highly elliptical orbit, but looking at resource identification, using the sail not as a propulsion system, but rather as the reflected energy source in order to get signals into its instruments. The last one in there is NEA Scout. It will also use an 80 square meter solar sail, but in this case for the propulsion, to go off and do proxops and rendezvous with an asteroid with a 6U CubeSat at about 3.3 to 0.5 AU distance. And there's a number of different asteroid targets that they're looking at. Last but not least, Resource Prospector. Resource Prospector, as we've been advancing all of our in situ resource utilization on Mars, we also realize there's a lot of technology risk reduction that we could do even on the moon. So Resource Prospector is a pre-phase effort that we're looking for an international partnership, actually with JAXA, for a lander that would actually go to the polar regions of the moon and test next generation prospecting and ISRU technologies for us in a very cost-effective way. So it's an extremely low-cost mission. I believe Dan gave a talk on it the other day. So encourage you guys to take a look at that. And we're looking forward to finalizing some of our partnership arrangements with JAXA later this calendar year. I won't go over the Mars 2020 since Jeff already covered that. And here's an image of Medley 1. And I talked a bit this morning about, and all these things we do and how we figure out what we're going to partner on and how we're going to acquire a capability. A lot of that's informed by a lot of these RFIs and BAAs and such that have been out there on the street. So we really do take these seriously, and we've been putting them out, and we will continue to put them out as a series in different areas to try to understand where is the intersection between when can we use commercial acquisition style, I mean things like COTS, where there is a market that's beyond what the NASA can provide, and where can we use commercial like terms, which is a slightly different shift where we can procure things with very little insight and oversight, but we're still paying them the lion's share of the cost because there's not a market for it, but we can acquire that capability different, versus where are the things that we inherently need to do inside of NASA to then keep on advancing those capabilities. And the whole plethora of these RFIs, RFPs, and BAAs out there help us try to figure that out. So it's really important, and we thank you guys for your feedback on a number of those. So with that, I am going to turn the stage over to Nantel, and he's going to do a bit of a deep dive on our most recent announcement related to public-private partnerships, and that is our Lunar Catalyst effort.
Hello, I'm Nantel Suzuki. As Jason explained, I work for him and for Chris in the Advanced Exploration Systems Division in HEO at headquarters. So I'm going to talk to you about this initiative called Lunar Catalyst. We're trying to do something a little bit new, a little bit experimental, if you will, but in keeping with some of the philosophy you've heard from Jason regarding our office, looking for new partnerships. And so I will dive a little bit into this and look forward to discussion afterward. Oops. So first of all, addressing why we're doing this, and I'll explain in detail what the initiative consists of, but we're looking at commercial lunar landers, and that begs some questions probably. First of all, what do we mean by commercial? That's an oft-used term. Essentially, I boil it down to a model whereby we're looking at fixed price goods and services in a normal commercial environment, and also the customers that are supplying this are not just, it's not just NASA, it's non-NASA customers. We might even say non-government typically, but actually in this case we might be looking at commercial providers for robotic landers that approach other governments as customers. So I'll just say non-NASA at least. So it's not NASA funding all of this. Otherwise, we could just go ahead with a traditional cost-plus contract, perhaps. But we're looking at a new model, and so commercial landers. Now, why the moon as well? Is NASA still interested in the moon or not? Although our focus is on, of course, these capabilities you've been probably hearing about through the week, and widely known, heavily focused activities in exploration, which is Space Launch System and the Orion vehicle, trying to develop capabilities in the lunar vicinity. The moon is still part of our exploration plans and sphere. In particular, we have interest, not just within the human exploration realm, but the science realm, using the resources of the moon potentially for solar system exploration, doing technology demonstrations in the lunar vicinity or even on the lunar surface potentially. And we also recognize there's a lot of international interest in the moon, and potentially commercial capability to the lunar surface would be of great help to an integrated architecture, whether it's for NASA directly or NASA's partners. So the model, the commercial model, NASA's been dipping our toe in this area for a number of years now, going back to about 2006 with COTS and commercial crew. What we see, in recent years is an increasing interest in space transportation out to the lunar surface. For example, the Google Lunar X Prize stimulated a lot of interest, certainly. Of course, that's a private prize and independent of NASA, but NASA certainly welcomes prizes like that, anything to help cultivate innovation or entrepreneurship. So there's a lot of synergy there. So that's the environment that we see outside of the agency. And so this is a new opportunity, certainly in keeping with the themes that you've been hearing from NASA a lot recently: sustainable and affordable exploration. So this type of project, this initiative to go to the lunar surface with commercial capabilities is kind of where the rubber meets the road, as far as one approach to achieving a sustainable capability. After all, a company that's in fact profitable by definition is sustainable. So we've been hearing lots of details on technologies. This initiative is a hybrid of both technology and partnership approaches to lowering the cost of exploration. And it's in keeping with all our policies. There's a quote from the National Space Transportation Policy. It's really embedded, commercial programs are really embedded into the National Space Act itself. So it's inherent to what NASA is directed to do. I'll just show this chart. You've been hearing about the Global Exploration Roadmap, no doubt, and this is just to point out that fundamentally there is an intent in the Global Exploration Roadmap to accommodate and encourage commercial participation. This is the mission scenario chart from that document, which has some hooks for sort of generic potential commercial opportunities that aren't particularly defined in that roadmap. Catalyst is one example of a sort of a commercial opportunity for robotic precursor missions to support the overall exploration roadmap. And even in the goals and objectives that the international community has bought into, these common goals that a dozen or more space agencies have bought into. Here are a few of them listed. Things like obviously developing exploration technologies, but also stimulating economic expansion. something like Lunar Catalyst, these commercial models are obviously very much in keeping with that. One of the objectives within that goal is to provide opportunities for the integration of commercial transportation elements into the exploration architecture. That's exactly what we're trying to do. Even things like engaging the public in exploration, there are lots of opportunities, I think, for participatory exploration once you incorporate a commercial model for going to a place like the moon. And so we've been looking at that with the private sector. A little more background, and Jason's touched on this already. We are approaching these partnerships, sort of public-private partnerships, with a lot of experience on the NASA side. Most recently, the Mighty Eagle and Morpheus testbed activities. Mighty Eagle was born out of our science directorate's interest in an international lunar network, ILN, and so we made a lot of technology advances with that testbed. Here you see some pictures of Morpheus flying as well, which has really improved our understanding and lowered risk in a number of technology areas. And so we've got this expertise, and we're ready to lend that and share that to the private sector. And so the way we've done it is through a competitive approach. That's what Catalyst is about. We had a couple of other examples here of lunar commercial tests, if you will, dipping our toe in the water. We had something called ILDD, Innovative Lunar Demonstrations Data. So this was a data buy where we entered into contracts with 6 companies and agreed to purchase lunar data upon we'd only pay purchase upon delivery of the data, and we've structured it as an IDIQ contract in successive data request stages. So we started an initiative, and that's that was kind of our first foray into a commercial model, and now we're trying something a little more. We started with an RFI last year to see if there was interest from the private sector, and yea, verily, there was. And the ground rules here were that these would be in-kind contributions. We're not throwing money across the fence, so to speak. So in that sense, we're deviating a little bit from what COTS and the commercial crew programs have done. But nevertheless, the expertise, the in-kind contributions that we're providing, private sector has shown great interest in it. It's helping them to advance their cause. So we released an announcement at the beginning of the year in January, and I think I've covered these points really, but there you see kind of the schedule. We collected proposals in March and selected partners at the very end of April. So since then, we've been in some agreements over some details on the Space Act agreement. So these are, again, no funds exchanged Space Act agreements that we're entering into. But we're very close, I think, to initiating, finalizing the Space Act agreements and initiating the partnerships. Yeah, I mentioned the no funds exchanged Space Act agreements. We didn't go in with any particular number of agreements that we were planning, but we ended up with 3, and I'll discuss that here in a moment. Let's see, the third bullet there is I want to touch on. NASA currently has no specific requirements for commercial lunar transportation services. So that's an important point. If we had requirements, what we would have done is put out an RFP or BAA and cut contracts. We certainly have plans, though. Jason just mentioned the resource prospecting, expedition, and resolve payload, and HEOMD is certainly interested in understanding the resource potential of the moon. The baseline plan, as Jason explained, is for the lander for that mission is to look at international partners, or JAXA in particular, is who we're talking to most seriously. As a backup, potentially, an industry lander capability could support that mission, but that's not the baseline. It would depend on the timing. But beyond that particular resource prospecting mission, we anticipate the potential for additional missions downstream. So resource prospecting indeed is one of the drivers and the drivers behind wanting this capability. Other mission drivers from NASA, sample return, for example. This was identified by the Planetary Science Decadal Survey. South Pole Aiken Basin sample return. Geophysical network deployment is also a high priority science activity. That's what the ILN activity was going to be addressing, and technology demonstrations as well. NASA did not stipulate any particular size to these robotic landers. We did note in the announcement some representative classes, small 30 to 100 kilogram, medium 250 to 500 kilogram payloads to the lunar surface. But these were just for information or background and not used at all as an evaluation criteria. Essentially, we were telling proposers, you identify for us what you think, where you think the sweet spot is for to support a commercial plan, and if you can defend that, then NASA will do what we can to support and stimulate that and facilitate that. Okay, these are just the how did we choose these partners, these selectees? We essentially these are the evaluation factors. Essentially, it's a combination of technical criteria and financial. So, do they have a sound technical approach and experience and so forth? But also, and very critically, how healthy are their finances? Their finances in the near term to actually hold their end of the partnership with NASA and be able to actively develop a lander capability, and also in the long term, what's their commercialization strategy? Do they really have a viable business plan? Do they have customers identified? What kind of investment have they been able to raise, equity or debt investment? So we looked at all of that. The draft Space Act agreement, we issued a sample agreement, and then proposers commented on it. And so these are things like, what kind of milestones are we going to be judging these partners by? And we'll use those milestones essentially as gates. If if the partnership isn't making progress and isn't achieving milestones which they themselves have identified, then we would judge it's not an effective use of government funds. But if it is making progress, then we'll continue. We didn't have any specific initial operating capability date for a lander that we prescribed, but these are 3-year partnerships, and we expect them to make substantial progress in that time, if not get all the way to the moon. And just for reference, the Google Lunar X Prize due date or deadline is the end of next calendar year, 2015. So these companies, 2 of them anyhow, are part of teams or have teams that are vying for that prize, and so they're certainly motivated by that, as well as their long-term business ambitions. So we did select 3 partners based on their likelihood of successfully developing a capability and a realistic financial strategy, as I mentioned. And our side, what NASA's providing, the in-kind contributions that I mentioned, specifically civil service technical expertise, very much in keeping with the AES division's philosophy and approach. Test facilities, so allowing them access to NASA test facilities at no cost, equipment loans, software, and as I mentioned, 3-year partnerships, which we hope to be initiating very soon. So here are the selectees. We're just, like I say, we're about to sign agreements very soon. So I can't get into details on their capabilities, but I encourage you to go to their websites or address them directly for details. But Astrobotic Technology with their Griffin lander, Mast and Space Systems with the Zeus lander you see there, and Moon Express, their MX-1 lander concept. So we're very excited to be working with all 3 of these partners. We will be working with them. Again, we have to bear in mind this is a public-private partnership. So we'll be firewalling information between the 3 and being very careful about proprietary data and so forth. But at the same time, we may look for opportunities to develop a community amongst the lander developers. And we'll explore that in the interest of sort of in an NACA inspired approach or model, promoting standards, identifying key technologies that perhaps our gaps between the technologies we need and the technologies available and the capabilities that we need to fulfill exploration objectives. So we'll explore the potential for community forums as well going forward. So that's Lunar Catalyst in a nutshell. The URL is there for more information. Like I say, it's sort of an experimental model, and we're just getting started and looking forward to rich interaction between NASA and these partners. Thanks.
Okay, so you've heard broad overviews of our main space technology programs, and we've gone into some more detail on some recent flight experiments to enable intradistant landing systems from Mars and an innovative approach to involving the commercial sector in developing lunar landers. So with that, we'd like to open it up to the audience for questions to the panel. So are there any questions? Sir.
I've seen indications that telerobotics is becoming more prominent in the pathways to Mars. And I didn't see that listed as a technology development by either machine. So can you talk about that?
Do you want?
Yeah, I mean, in general, yeah, telerobotics is, there are going to be periods of time during our architecture and human exploration where we're going to have periods where it's going to be human-tended spacecraft, either in space or on the surface, where we don't have humans there at 100% of the time. So there are been significant investments in telerobotics, and we've been trying to boil it down to a couple capability systems. Obviously, with the station today, we have very capable robotic arms and manipulators up there on the outside. And then inside, we've been looking at advancements in humanoid robots with STMD, with Robonaut, along with the space station colleagues there. Our Spheres platform, which was co-developed with DARPA a number of years ago. We've been testing free-flyer, robotic free-flyer type work, among other things with it. And in fact, STMD is going to be building the next generation version of robotic free-flyers on the surface. And all those are autonomy. And at the same time, telerobotics operations, say a human in orbit around a planetary surface, controlling robotics on that surface. There have been numerous demos. In fact, there's a demo going on today or tomorrow with ESA called Metaron, where our NASA folks and ESA have been working together on telerobotics operations from the space station to controlling robotics at ESA in Germany in this case. And we've also done other demos where controlling station crew members controlling and doing telerobotics with robots out at NASA Ames. So yeah, there is a significant amount of investment in telerobotics, autonomy, and autonomous robotic systems. But we do a lot of things. It's hard to highlight everything. So
That's a good summary by Jason. We are in our part of the org have been pushing forward the Spheres work that he mentioned, which are free flying devices that have been a lot of testing of those on station, as well as telerobotics, station crews operating a rover at NASA Ames.
Okay. Other questions? Sir.
Hey, Mark, just on the parachute test. I mean, you had the China Lake experiments. I mean, what was the disconnect between what you learned there and what happened in real time? Maybe I missed something in the big picture there. Were they that far apart? What did you learn in China Lake that somehow didn't apply with that?
Yeah, so that's a very good point, Leonard. The tests in China Lake are designed to test the parachute at a particular point in its operation. Our assumption had been that the peak loads that a parachute experiences is in a supersonic flow is at the moment of full inflation. And so the test at China Lake is designed to get the parachute into the state of full inflation and then yank on it with 100,000 pounds. And so that test is only designed for that moment in time. The failure that we saw in the test, the supersonic test, was a much earlier in the deployment event. So it was just as the parachute was opening, we started to see rips in the disc of the fabric, just as it was starting to come open, long before it got to full inflation. So it's a completely different mode than the one that we had been expecting.
And any solution for that?
Yeah, we have, we already, because we got such great data, we were able to very quickly identify and understand what the problem is and come up with solutions. We've already been talking with the parachute contractor about what to do for the next one. So I think it's the data has been fantastic, and that's what makes this really valuable is we know exactly now what to do.
Another question? Okay, well, thank you all for coming. That's the conclusion unless anybody has a last question. Sir, yeah.
Maybe just a follow-up then. You know, you have limited dollars, maybe for you. Are there things that are still priority, but the money is thin? Can't do everything, but what would be the next picking order of things? What would you like to see some money spent on that could have a high payoff,
Oh, well,
other than everything?
well, okay, that question can be answered a lot of ways. There's certain projects we have where what we're always looking to do is the minimum, especially when we get to the demonstration, which are pretty expensive projects. It's like Mark's project here. We're trying to do the minimum we need to do, but still deliver a technology that's ready for infusion. If we do a bunch of stuff and we don't get it to an infusion point or nobody wants to use it, then you could ask questions about the value of that investment. But so we have a number of projects where we've de-scoped them because of resource limitations to the point where it kind of hurts a little, and we wish we could do one more thing. In fact, Mark's project in particular, we de-scoped one flight test already from that. So he had the shakeout flight this year and then 2 more next year. There originally were 4 in the plan, and so to still do just enough, but maybe we would have liked to have done a little more. We've de-scoped that. Other projects, similar sorts of stories. There are other investment areas where we really haven't been able to do anything real significant yet, but that I think are begging for more serious investment. One that I personally think the agency really needs to invest in is nuclear thermal propulsion. Now, Jason's org is doing the fuel elements, and he highlighted that. But there's a lot of other capability we need to recover from what we did in the 60s and then extend. We gave a briefing from our mission directorate to Charlie Bolden in about the March timeframe, where we looked at propulsion options. We really utilized a lot of the work that Human Exploration's mission directorate has done, looking at different architectures over years of that, including their more recent work on the Evolvable Mars architecture. And you could very reasonably conclude that sustained exploration of Mars, meaning we want to set up shop, we want to go back, and we want to go back again, we want to go back again. And we want to be a little less at the mercy, literally, of planetary alignment for when we can go and when we can come and go. Sustained, serious exploration of Mars begs for nuclear thermal propulsion, and I think, or some other advanced propulsion, like say nuclear electric. But if you compare the two, nuclear thermal is something that we could invest the resources and have that in a decade. Nuclear electric has a lot more really big technology hurdles before we're flying that class of megawatt nuclear electric propulsion. So there's an area where in STMD we talk about wanting to invest, but addressing either nearer term needs or needs that are more specifically in the architecture at the current moment. We just haven't got to that. So there's a number of things like that we could list, but that's one that's, I have a propulsion background, so that one's kind of near and dear to me.
Sir?
Jeff, with the shutdown of SRTG under Jim, where does the agency see us moving to kind of bridge that gap prior to moving into RTGs or others, given the nuclear plutonium issue and that kind of, where do you, how do you fill that gap with the demise of SRTG?
One of the ways, there's been a lot of discussions about that. There's a working group at headquarters that's been looking at that issue. Chris has been engaged in that quite a bit, and the small fission activity that we highlighted is one of the projects that we're working in conjunction with Jason and Chris's organization to try to address that. That can be used for spacecraft as well as surface power. And so the notion, I think, is to look at implementations that can serve more than one purpose and try to come up with a general approach that, just as a matter of scale, can be used for several hundred kilowatts on up to a few ones of kilowatts, maybe even to 10. Is that a good...
Yeah, we're doing a study between our space science mission directorate, our space technology mission directorate, and human exploration to identify the needs for small fission power systems. We're looking at 1 kilowatt class power systems to replace RTGs. We're trying to see if we could cluster several of those together to meet the higher power levels needed for human exploration, which are primarily to power in situ resource utilization systems on Mars or provide power to the habitats. We're not certain there is an overlap, but we are currently studying that. And if that looks positive, that it meets multiple mission needs, then our space technology mission director would start investing in that. Okay, other questions? Well, we thank you for your interest and appreciate you coming.